Hello everyone, let's continue on the topic of capillary pressure, and in this video we're going to do this example which is related to the displacement pressure and the concept of the capillary pressure. Alright, so let's see what the example is. You see a table here, and in this table the first column tells you the pore radiuses. So you have a core sample and you analyzed the pores inside this core, and you realize that the pores inside your core are 1 micrometer, 2.5 micrometer, 5, 10 and 25 micrometer. So these are the pore radiuses or pore sizes that you have. Now on the right side there is individual pore volume, which means that each of your 1 micrometer pores, this is a fictitious sample of course, each of those 1 micrometer pores have this much of volume, for example 3.14. Each of those 2.5 micrometer pores have 19 micro cubic meter volume, and so on and so forth, right? And then the third column is the pore number. It means that how many of these pores with this size is inside your fictitious core. So it's 10,000 for all the cores. So therefore, if you want to calculate the total volume of the pores which have a 1 micrometer radius, then you just multiply the number of pores with the individual pore volume. It gives you the total volume of each pore, right? Okay, so we have this information, and based on that you can calculate the contribution to the total pore volume, right? How do you calculate the total pore volume? You just add all the volumes that you have here, right? This is the total pore volume, and then if you divide each of these by the total pore volume, it gives you the percentage of the contribution of each of these pore sizes to the total pore volume. And then you see another number here which is called displacement pressure, and displacement pressure, you can see it starts from 70 for micrometer, 70 kilopascal basically, and it starts from that number and drops to the lowest value, which is 2.8 for 25 micrometer pore radius. Now the question is, what is the minimum? Let's assume that this core sample is initially 100% saturated with water. Okay, now you want to and your pores are all water wet. Now you want to inject oil into this pore, into this core sample, and you want to displace all the water from this sample. Okay, kind of what you saw here. Okay, initially let's assume these pores, 25 micrometer and so on and so forth, are filled with water, and then you inject oil. You want to displace the water out of these pores. What is the initial displacement pressure? What is initial? See the difference here compared to what we discussed previously was displacement pressure. Here it says initial displacement pressure, and what it means is that the initial pressure that you can displace the water from the core sample. There are some pressures that if you apply, for example, to your oil and you want to displace the water, you will see that no water will be displaced from the core sample, right? Now there is a threshold pressure, which at that pressure, if the oil injection pressure reaches to that pressure, then you start to remove water from the largest pores because they have the lowest capillary pressure or displacement pressure. Okay, so by looking at this table, you will see that the lowest number is 2.8 for the largest pore. Of course, you see the trend. The largest pores have the lowest displacement pressure. It means that if you inject your oil with a pressure equal to 2.8 kilopascal, then you will be able to remove all the oil from the 25 micrometer, remove the water from the 25 micrometer pores. Okay, if you increase your injection pressure to 7, then you will be able also, your oil will have access to the 10 micrometer pores as well, and it will displace the water from those pores. And if you increase your pressure highly to 70 kilopascal injection pressure, then you will have access to these 1 micrometer pores as well, so you will remove the water from those pores. And this is what it means. So initial displacement pressure in this case is 2.8 kilopascal because you will be able to remove the water from the largest pores by if you apply 2.8. Now if you apply 2 kilopascal, then you will not remove anything from the core sample. All right, so this picture is related to that example still. Look what you see from this picture. So the x-axis is the water saturation. Remember the definition of water saturation. Water saturation was equal to the volume of the water inside the pores divided by pore volume, right? And there is displacement pressure. So what does this picture or figure tell you? It's displacement pressure. So if you inject the oil with pressures lower than 2.8, again, for example, 2 kilopascal, right? What happens? How much the saturation of the water? So again, let me draw it here so we have a better understanding of what's going on here. So this is our core sample. We have several pores with different sizes. So we have small pore, a little bit larger, and let me just draw a couple of pores here, right? And I'm gonna try to paint it so it's different from each other. So this is, let's say, 25. Let's say this is 10. And let's assume that we have a 5. Right? The sizes, of course, are not, the scales are not correct, right? And 2.5, and just let's say this is the 1 micrometer pore. All right. So you inject your so these are all pores filled with water, right? Then you inject oil into this system. And then you want to remove these waters from the core sample, right? So let's say you are injecting initially at 2 kilopascal. Can you remove any of these water from the core sample? The answer is no, because minimum pressure that you require to displace any water from this core sample is 2.8 kilopascal. So what happens to your water saturation in this case? Doesn't change, right? 100% initially. Now let's increase the pressure to 2.8. Second one, 2.8 kilopascal. And what happens to your water saturation? First, 2.8, remove all the water in the largest pores. So these waters will be displaced with oil, right? All these waters will be displaced by oil. Now, what does it mean? It means that how much is the total volume of the water inside the 25 micrometer pores? 82%, right? So by injecting oil at 2.8 kilopascal, you will displace 82% of the water out of the core, and you substitute it with oil, because with that pressure you can remove all the water inside the 25 micrometer pores, which they contribute 82% of the total water of the core sample, right? So what happens? Your water saturation drops by 82%. So your new saturation is 100 minus 82.5. Sorry, I'm going over this. So this is going to be your new saturation, right? So if you look at this picture, you see that if you reach this minimum displacement pressure, until you haven't reached that point, your water saturation does not change. It stays 100%. Once your pressure increases to 2.8, then you will lose 82%. 82.5% of your water saturation, and you will get to this point. So your new saturation is around 27.5%, or yeah, your new saturation would be around 27.5. So this is not 100%, I guess, accurate. All right, so now what's next? Then you increase your pressure, right? To what? To 7. So if you go to the 7 kilopascal, then you will remove all the water which are in 10. So let's say this was 10, right? So you will remove the water, you substitute it with oil, right? How much would be your new saturation? So you already lost 82%, right? If you remove the water from 10 micrometer pores, you will lose another 30%. So your new saturation would be 100 minus 82.5 minus 13.2%, whatever that number is, right? So you will lose another 32% here. So you'll get here. I mean, you increase the pressure, so of course you get there, right? Increase the pressure. And just keep going. Do the same thing, increase the pressure, calculate the saturation. You will get to a curve which is called the displacement pressure or capillary pressure curve, and that's exactly how they do it in the laboratory. So when they want to measure the capillary pressure, or they want to find the capillary pressure of a specific core sample, they fill it with water, and they usually inject air, and they displace keep increasing the air pressure into the core sample and calculate the water saturation at each step, and then they can develop this this displacement pressure, right? Okay, so we defined the free water level previously. That's where the capillary pressure is 0, right? And we defined the oil water contact as the depths at which you will see oil from that depth. Okay, for example, if you look at these curves here, so this is a capillary tube. Inside here is water, here is water, here is oil. This is oil water contact. Inside the capillary you have this, and here is another example. This is a different rock, of course, and then in this case this is a oil wet rock. Can you say why? And this is a water wet rock. You can see that the oil tries to attach to the surface more than water, and then the water do not rise inside the capillary as much as this case, right? You can see the water attaches to the surface of the capillary. Anyway, so this is a water wet case, right? In the water wet case, this is called the free water level. And if we are looking into the capillary, this is called oil water contact, because inside that capillary you can see the oil from this point. So this is called oil water contact. In this case, this is our oil water contact, right? And this is the free water level. So in an oil wet reservoir, the free water level stays above the oil water contact. However, in water wet reservoirs, which are most of the cases, we have a water wet reservoir, the oil water contact is above the free water level. Okay, and in the free water level, the capillary pressure is 0. It's shown in this picture, and until you reaches the displacement pressure, your saturation stays 100%, and then you have this type of curve. This is called the capillary pressure curve, right? In this case, it's drawn as a function of depth, and I will tell you how to convert the capillary pressure to depth in the next video.